Hello everyone, and welcome back to this week in Algebra 1 and linear inequalities. We're going to move to a slightly different topic where we're going to be talking about linear inequalities still, but we're going to be talking about them in standard form and a little bit of practice on how to manipulate those standard form, in this case inequalities, in order to be able to graph a little bit easier. So we're going to go ahead and practice that in these first two examples. And I'm starting off with 4x plus 5y is less than or equal to -5. And I already have the graph there. I'm not necessarily worried about the graph here. I'm just worried about refreshing our skills on how to convert the standard form inequalities to something that would look like a slope-intercept form with our y, mx, and b. So we know that we want to get the y by itself in this scenario. So it would make sense that since our left side has two terms, 4x and the 5y, it would just make sense to go ahead and start off by subtracting the term that we don't want to keep over there. We want to keep the 5y, over there. So I'm going to go ahead and subtract 4x from both sides, and that would leave me with 5y on the left side is less than or equal to -4x minus 5y. And I put that in that order. We know from -5 and -4x are not like terms, but I put it in that order just so it starts looking like our slope-intercept form with the mx before the b. I need to wrap it up. I still want to isolate this y, that variable there. So I'm going to go ahead, and since it's 5 times y currently, the inverse operation would be to divide 5. It's almost like distribution here, where kind of like multiplication, but we have to divide 5 from everything. So that would leave us with y is less than or equal to -4/5 x minus 1. And we have that linear inequality in slope-intercept form now, so we're happy about that. And you can take a look to the left side, how those things would match up, specifically the line. And specifically with the line, we see our arrow here has that bar underneath. It's less than or equal to, so that's where we would get our solid line from. And as always, we want to make sure that we check a test point in this problem. I already went ahead and did that. We have video on that earlier that hopefully you checked out in order to graph and get that graph over there. I want to move on to this next problem, and I want to do this next problem specifically because there is a small trick here. One of the more trickier things that we talked about back in our inequalities unit. So I have 3x minus 2y is greater than -6. And I'm going ahead and start off error analyzing myself here by realizing that that arrow does not have a line underneath it. So we got to make sure we put a dotted line here on our graph. And let's go ahead and try to do that. That's a little bit better there. Again, that focus there was because we see that arrow without a line underneath it. It's just greater than. So I need a dotted line right there, not a solid line. It's one of the big changes to the linear inequalities unit that we've talked about in previous videos. So what I want to do here, same process, is I want to try to isolate that y variable. And I'm going to start off by moving the other term on the left side, and I would subtract 3x from both sides. That would leave me with -2y on the left side and -3x minus 6 on the right. Now I need to slow down here for a second because we're about to do something that we've talked about in the inequalities unit that you might say to yourself here, well, I remember that, but looking at it right now, maybe it's not something that you remember. So I'm going to go ahead and I'm going to divide that coefficient in front of the y, which is -2. And that's a big deal. If you're in one of my classes, you know why I just wrote that in red. If you were in one of my classes, we called that the red alert. We're talking about inequalities where we know that if we divide, which happens usually more of the time, or multiply by a negative to both sides, we know we need to flip the inequality symbol. I'm going to abbreviate inequality there. So with that being said, the math work here isn't the most terrible. We're going to go ahead and we're able to do this and finish this up, but we have to be aware that if we divide, and I don't think it's going to happen too much for us here this week, but if we divide by a negative to both sides of an inequality, whether that be with one variable like we did back in the day in one of the previous units, or if we're doing it right now, we need to make sure that we flip the inequality symbol. So when I wrap this inequality up, I have the y. I got a -3x over a -2. Negative over a negative would make a positive. And that happens again with the constants over there. -6 divided by -2 would be a positive. That one we can reduce. But I got to be aware of that symbol flipping. Got to be aware of that symbol flipping, and that happened because we divided both sides of our linear inequality by a negative number. All right, so you can take a look over there at the graph. Again, things that we would check out. We would check out our test point in order to know where we were shading. I checked 0, 0, which is one that I recommended in the last video that you do. It does work out here that the side of 0, 0 does work. And again, it does work for either up here or down here. 0, 0 would work for either one of those. So want to go ahead and if you wanted to practice that, you could pick any of the other points there in the shaded region, make sure it works out. Next up, I want to just talk a little bit here about some word problems. And just first and foremost, I guess, how to set them up. So it says a catering company has small tables and large tables. Small tables seat 3 people and large tables seat 5. They are planning a party for at least 100 guests. How many of each size table can they use? So if you have any familiarity with a sporting event, I think in this type of a problem, what we're going to see here is that there might be a situation where we have at least 100 guests. And I mention a sporting event because we know that from previous units, the word at least, or the phrase at least, I should say, means that the smallest amount, at the very least, there will be 100 guests. So we know that we could have 100 guests exactly. Or we could have more than 100 guests. All right, so this is going to be the greater than or equal to symbol here when we do this problem with 100 guests. So I think of sporting events because of standing room only, then the possibility that this party could potentially be 1,000 people, which is, you know, ridiculous considering it says at least 100 guests. So some people might not be able to have chairs, but we're shooting for the over here or equal to. So we have 2 different variables here. I see small tables, I see large tables, and I see that the small tables seat 3 people, and the large tables seat 5 people. So you can certainly use different variables here. I like to use x and y just to keep it the same. But what I'm setting up a linear inequality for this, we know that 3x plus 5y, we're going to bring in that greater than or equal to symbol here, is greater than or equal to 100. All right. Now, if there were 0 people, well, let me start off here by just kind of labeling some things for you here. Our x value here would be the number of small tables. I'm going to abbreviate the word small. And the y value is going to represent the number of large tables. And we get that from our inequality right there. Now, I just want you to take a look at that real quick and realize that that inequality is there, that greater than or equal to. So, you know, we could come up with some ridiculous numbers. If you were to say there would be 1,000 small tables and 1,000 large tables, yeah, of course that's going to be able to sit at least 100 people because there's more tables than there are people.
Okay, so for this last problem, we have ourselves another word problem, but there's a graph off to the side also. You receive a $75 gift card to the bookstore. Hardback books cost $10 and paperback books cost $5. So write a linear inequality. This one's a little bit different from the previous one because we're receiving this $75 gift card to a bookstore, and that is the total amount of money we have here to spend at the bookstore. Our two things that are unknown involve our hardback books that cost $10, and we know we have paperback books that cost us $5. So I'm going to go ahead and I'm going to call the amount of hardback books X and the amount of paperback books Y. And when I create a linear inequality, I'll let that total be on the right side. It's kind of how we're used to seeing it here in standard form. So when we write this out, it would be 10x plus 5y. And we know the total here is $75, but we have to think about inequality-wise what we would use here. Now, we can't use that gift card and purchase something for $100. You'd have to bring in additional money other than the gift card for that. However, you are certainly more than welcome to go to the bookstore, buy only one book, and that would not necessarily be the whole gift card. Using the gift card, you'd still have money left over for that. So we're allowed to spend exactly $75, and we're also allowed to spend less than $75. So we have 10x plus 5y is less than or equal to 75. Now, we do want to make this and manipulate it into something that looks like slope-intercept form, so it's a little bit easier to graph, and we'll do that. And again, we're getting that y by itself, so we'll start off by moving the other term on the left side. That's subtracting 10x, and we get 5y by itself is less than or equal to. Again, we'll want to make sure we try to make this look in slope-intercept form as much as possible. We can't combine those. Those aren't like terms. We'll divide everything by 5, and we'll come up with y is less than or equal to. Negative 10 divided by 5 is negative 2. X, and then 75 divided by 5 would be 15. So we got y is less than or equal to negative 2x plus 15. We'll go ahead and graph that. And when we graph that, we'll start off with our y-intercept is 15. And we're going to go down 2 and to the right 1 each time. Again, hopefully this is a little bit of review for you when it comes to change around a standard form problem to one that now looks like it's in slope-intercept form. And we're good to say that we know we have a solid line here. So I'm going to go ahead and straighten it out a little bit here. That looks good. And we have our line. Now it's definitely a solid line. Okay, we learned that in a previous video. We have the line underneath there. We have that or equal to, so it's a solid line. And we can go ahead and shade in. We want to check out a test point. And in this situation, looking for a test point that is not on the line. So I'm going to go ahead with our old from the origin 0, 0. I can take that and plug that into the original inequality that we set up, or I can take that and set it and put it into the one that we manipulated to get into slope-intercept form. Either way, it's perfectly fine. I'll go ahead with the second one here and plug in our 0, 0 since it's not on the line. -2 times 0 is 0. And we come up with 0 is less than or equal to 15. This is a true statement. 0 is smaller than 15. So we're going to shade on the side of that point that we use as a test point. Now, hopefully one thing you notice about this particular graph is that we only have the first quadrant. And hopefully we recognize here that because there's no such thing as a negative amount of hardback books or a negative amount of paperback books, we don't have to necessarily worry about any negatives here. So I'm labeling my two axes here, which we did at the beginning of the problem, but it's going to help us when we get down here to the bottom and have to answer some more questions about this. The next question says, if you were only purchasing hardback books, what is the maximum books you could purchase? So we only want hardback books, which means we would not want any paperback books. So since we do not want any paperback books, that means in this situation, y is going to be 0. We don't want any paperback books, only hardback books. So I can take the number 0, plug it in for y. And I'm going to do that because if you go ahead and take a look over here, we're looking at where y is equal to 0, and it's over here on our x-axis. And it kind of looks like 8, but it's not quite there at 8. Could be somewhere in the middle. If that line's not straight, you can kind of see the line right here. It comes off the point a little bit. So it's always good to use the numbers to go ahead and plug in and gather up that information. So again, we can pick either one of the two inequalities that we have. I'm going to just practice plugging into the original one here. We'll have 10x plus 5, and the y we said is 0. No paperback books here. And 5 times 0 is 0, so we have 10x is less than or equal to 75. We divide both sides by 10, and we get x is less than or equal to 7.5. Now, there is no such thing as half of a hardback book, so for this question right here, our maximum amount of books, if we're not allowed to purchase any paperback books, can't be 7.5. It doesn't quite make it to 8. The only whole number that would work out for this inequality right here, or the largest whole number, I should say, that works for that would be 7 hardback books. Last one up here, it says, what is the maximum amount of books that you can purchase? So we know that anywhere here in our shaded region are solutions. So for instance, it is possible for us to only have one of each type of book. Because it's in the shaded region, it's possible for us to purchase maybe one hardback book and 6 paperback books. Anything in the shaded region is possible. However, what I need to consider here is the maximum amount of books. And we know that any point on our solid line counts. If we had a dotted line there, so if this was just a less than symbol, it would be a dotted line and it would not count. But it does count here. And I say that because that's kind of where our maximum locations are going to be at. You can see none of the green shaded area over here as I'm on the graph. None of the green shaded area goes past that line. So those numbers are going to be kind of our largest numbers here. And I'm going to check this out and take a look at some of the points here. And that point right there would be the point 0, 15. Makes sense. It's our y-intercept. We have the point 1, 13. We have 2, 11. And I'm starting to get a little off here. Let me try to reorganize these a little bit more. I have the point 3, 9. And you can kind of see as we're going along here, the total amount of books. So here we're not worried about whether or not it's hardback or paperback. It could be both. The total here would be 0 plus 15. So here, that's a total of 15 books. Here it's a total of 14, 13, 12, and generally speaking, that pattern would follow. So, as we would continue to go, the numbers would continue to go down, and there's no way anything in this green shaded region, like here, we talked about 1, 1 being a possible answer, but that's only 2 books total. We talked about 1, 6 being a possible answer, but that's only 7 books total. So if we're looking for a maximum amount here, the largest amount of books possible would be 15 books. And we got that really from looking at our graph over here. We said that all of these points on the solid line count as answers. Which one would give us the largest amount of books total? 0 plus 15 would be 15. Now, unfortunately, what that means is that we would have 0 hardback books, but we would have 15 total books. All of them are paperback. That would be the largest amount of books we could purchase at this bookstore with the gift card of $75 that we have.